Sketch the direction field for the differential equation y prime equals x squared plus y squared minus 1. Alright, we'll need to compute the slope at several points. And to do so, we're going to have to substitute in various values of x's and y's. This is a lot like what we did when we first learned how to sketch a line. We chose some values for x, substituted them into our linear equation, and as output we had some y's, and we plotted points. The difference here is we can choose any x's we wish, any y's, and we'll get out a y prime. And we know we can choose any x's, any y's without restriction, because if we look at our differential equation, we see that no matter what real number we choose for x, what real number we choose for y, we can square them, sum them, subtract 1, and we'll get a number out as our output. So let's choose some that are fairly close to the origin so we can see if there's any interesting behavior going on near the origin for our various curves that meet the requirements of this differential equation. And for instance, if we pick an x of, say, 0 and a y of 0, let's see what's happening at the origin. And so we substitute 0 for x, 0 for y, and we subtract 1, and we get out a negative 1. That's our y prime. So we know that the slope at exactly that point will be a negative 1. If we choose another one, say, if you look toward the far right, our x is 2 and our y is 1. Well, if you substitute in, you'll get a y prime of 4. So we continue and pick a bunch of different values, going off, make sure to choose some positives and some negatives, some that are slightly bigger and slightly less, and then we'll be able to design our field. And the field is consisting of a bunch of little segments. And what do these segments mean? Well, if we were to choose one, for example, the first one that we picked in our table, 0, 0, x is 0, y is 0, you can see that our slope there, the slope of the little segment that we draw, corresponds to the negative 1, our y prime. And so anytime we want to draw one of these little segments to give us a sense of our slope at that point, all we have to do is look at the table that we've drawn and figure out what our slope is there and draw a little mini segment for that slope. So let's look at a particular solution. The way we would find a particular solution to this differential equation is we have a point that we begin with, let's say the origin, and let's find a function that meets the requirements of our differential equation and which goes through the origin. So we begin with a point at the origin. Now we take as our direction the slope of that little segment we've drawn. We found it was negative 1, but here the number doesn't matter so much. What matters is the direction that we're being pointed in. So we can either travel upward or downward. We'll do both, but let's first set out toward the right. So we follow the direction that's implied by our little segment, and we go downward, and as soon as we hit another segment, we take its direction, its slope, and so if it tilts a little bit, if the slope changes, we change the slope of our curve and redirect. If we hit another one that aims us upward, we begin traveling upward. And we can continue in this manner as far as we wish, or as large a piece of paper as we have. And then maybe we want to see what's happening on the negative values of x. So we set off upward as directed by our original slope of negative 1. And if we hit another segment with a different slope, we redirect. And as you can imagine, the more mini segments we have, the clustered closer together, we'll get a better approximation of what our curve should look like. And if we wish to start somewhere else, we can simply pick a point, take the direction, and sweep out some other curves that will work on our field.